Okay, so we have an example to do that will be similar to a problem on the test that comes from Chapter 8. So what I'm looking at now is example 3 called Torques and Angular Acceleration. It's on the PowerPoint that's posted under the current materials for the test. So examples 1 and 2 were solved during another video that's already been posted. That was a video that I recorded previously during a snow day, but I wanted to also do an example similar to the problem on Chapter 8 that will be on the problem solving test section of your test coming up. So I don't have a print off of this, so my hope is that you will open that PowerPoint and have the problem out in front of you as you are working. But I'm going to read it. So it says that a dad is pushing tangentially on a small hand-driven merry-go-round, and he's able to accelerate it from rest to a frequency of 15 RPMs in 10 seconds. We're going to assume that the merry-go-round is a uniform disc that has a radius of 2.5 meters, and it has a mass of 560 kilograms. And then there's 2 kids, each with a mass of 25 kilograms, that are sitting opposite of each other on the edge. And there's 3 things we're looking for here. What is the total rotational inertia of the merry-go-round when the 2 children are sitting on it? What is the angular acceleration of the merry-go-round? And then also, what is the torque required to produce that acceleration? So we have a couple of things going on. So this is example 3, where we need to figure out, well, I guess I'll draw this here. So here's my merry-go-round, and I have 2 kids that are sitting opposite side on each other that we will approximate just as being little dots here on the edge of the merry-go-round. The radius of the merry-go-round is 2.5 meters. And the mass of the merry-go-round is 560 kilograms. And the mass of each kid is 25 kilograms. And the other information that we have is that it accelerates from rest to 15 RPMs in 10 seconds. So there's a few things that you could do here. I'll start this in the order of that the problem asked me for. So the problem part A says, what's the rotational inertia of the merry-go-round when the 2 children are sitting on it? So we need to find I total. And I know that that I, rotational inertia, is always going to be the rotational inertia of all the different things that are here. So there's 3 things that are rotating around in this circle. I have 2 kids. So I'll say I kid plus I kid. I'm not going to label these as kids 1 and kids 2 because I want to make sure that I'm taking into account that those are both the same kid. So I don't need to label them as 1 and 2. They have the same mass. Sorry, they're not the same kid. Plus the rotational inertia of the merry-go-round. So we have talked in class about how to do this. This is a pretty hard rotational inertia question here, where it's not too many problems that we've done that have a more complicated rotational inertia than this. So each kid we're going to approximate as a dot. And the reason that we get to approximate them as dots is because nowhere within the kid is the axis of rotation. So if the axis of rotation is not within the body that is rotating, then we just approximate this thing as a dot. And on your equation sheet, there is a formula that says that I is the sum of all m(r) squareds. And this is the formula that you want to look to for this, where each kid has a mass and a radius, a distance that it is away from the axis. That's going to be each one of these. So kid 1 is m kid times r squared. R is going to be that same 2.5 meters, 2.5 meters that the kid is away from the axis of rotation, plus kid 2, which is another mk times r squared, plus the rotational inertia of the merry-go-round. And I don't have a print off of the table in front of me, but hopefully you do. It should be on your equation sheet. On the back-hand side, there is a bunch of rotational inertias, and we are looking for something that looks like this. So it should be a cylinder that's flat, going around in a circle. Pause it if you haven't found it yet. But when I look at this, I see that this is 1/2 mass of the merry-go-round times the radius of the merry-go-round squared. So that is the rotational inertia. And we're ready to plug in numbers. So I'm going to go ahead and say that this is 2 times 25 kilograms times 2.5 meters squared, so that I don't have to write that twice, plus 1/2 times 560 times 2.5 squared. I haven't done this one yet, so it doesn't look like you can see it anyway, but I have 2062.5 right here. The units of rotational inertia, we don't have any specific unit, any special unit for that, but it's a mass times a length squared, so it must be a kilogram times meter squared. And now I want to write this in the correct number of sig figs, and if I go back to the problem, looks like I see one of them is 3 sig figs, but all the rest of them have 2, so I will round that to 2 sig figs, which means I'm going to write that as 2100 kilograms times meter squared. That's my answer. In part B, now I am asked for the angular acceleration of the merry-go-round. So the formula for angular acceleration is that alpha, that's angular acceleration, is a change in angular velocity, that's delta omega, over the time elapsed. So that is omega final minus omega initial over the time elapsed. Omega initial I know because I know that it accelerated from rest. So that's omega initial. I know that it took 10 seconds, so that's t. I don't know omega final in the correct units because I know that omega final, that is the information that I need to get me omega final. But in order to use this equation, I need to have the angular velocity in metric units, which is radians per second. So I need to get 15 RPMs from rotations per minute to radians per second. So to do that, rotations in 1 minute, right, 15 rotations per minute. I'd like to get that to radians per second. So we'll get rid of rotations first. I'll say that 1 rotation has 2 pi radians. And that a conversion factor is on your equation sheet, though it's maybe one of those things that's hard to not memorize by the end of the semester. So I've got rid of my rotation unit, and I have my radian, which I wanted. Now I need to get rid of minutes, so I'm going to put minutes in the top so that my minutes will cancel. They're in the top and then the bottom, seconds in the bottom. 1 minute has 60 seconds, and now I'm left with radians per second, and I just need to plug this into my calculator. 15 times 2 pi divided by 60. Okay, and I have 1.5708 radians per second. So now I'm ready to plug this in for the final angular velocity, and I have 1.5708 for my final, minus the initial, which was 0, divided by the time elapsed, which was 10 seconds. And I have that divided by 10. I'm just going to move the decimal place once, so that's 0.1571 radians per second. Written to 2 sig figs, I'll round that to 0.16 radians per second. And so that is the angular acceleration. Whoops, I guess I have an issue with my units here. The unit of angular acceleration is not a radian per second, but a radian per second squared. And you can see that from my work here. So I'll put a little squared in there. Now I'm ready for the last thing, which says what is the torque that's required to produce the acceleration? And this problem has been set up to set you up for this last step, which is that torque is I times alpha. This is the rotational analogy to Newton's second law, where a torque is the rotational analogy to force. Rotational inertia is the rotational analogy to mass, and alpha, angular acceleration, is our rotational analogy to regular old acceleration. So this is like F equals ma that we have used before. So in the problem on the test, I will set you up in a similar way where I promise you that you will use this question on the second problem, the chapter 8 problem in the problem solving section. So make sure that you are ready to do that. It wouldn't be a terrible thing to write on an equation sheet just so that you remind yourself and don't get yourself confused and totally lost. There will probably be something where we have to either calculate or solve for an I, and something where we have to calculate and solve for an alpha, and maybe something where we have to calculate and solve for a tau. So that's what we're doing. We have already found I, it's this. We have already found alpha, it's this. We just need to multiply those numbers together. I'll go ahead and use my unrounded numbers so that I don't introduce rounding errors in my answer. And so that is 2062.5 times 0.1571. And that is 323. Well, I'll write it as 324. And the unit here, let's see what this unit should be. I have I, which is kilogram times meter squared, times alpha, which is a radian per second squared. A radian is a unitless number, so we tend to ignore that. So this is 320 kilograms times meter squared per second squared is the unit of torque. Excuse me, space. That's the unit of torque. The unit of torque is also, if you remember from this, torque is R times F, which is a Newton times a meter. So another just fine unit here would be 320 newtons times meters. Either one of those is just fine as your answer. The way that this works, a Newton is a kilograms, right? Newton, that's a Newton, is a mass times acceleration. So 1 Newton is 1 kilograms times meters per second squared. So kilograms times meters per second squared, we just have one extra mass to deal with. So a Newton times a meter is the same as kilograms times meter squared per second squared, and either unit would be just fine. This is the more traditional unit of a torque, so you can write it that way, but I wouldn't need you to memorize that. Okay, and that is, I think, the gist of that problem. So it seems like a lot, but remember to break it into the chunks as you go through it. And that where we are going is that you will definitely have to use this equation at some point. You will definitely have to think about the rotational inertia of something. There probably won't be 3 objects on your test that you need to add together, though I wouldn't put it past me to put something like this on as a multiple choice question where you need to calculate the rotational inertia given multiple bodies together. So that's a good thing to know how to do anyway.